Have you ever been sitting at a diner and you notice how a straw resting in a glass of water looks mysteriously broken right at the surface?
Oh, yeah. Like it's physically snapped in half.
Right, exactly. Or maybe you picked up a polished spoon, looked at the back of it, and noticed your face is warped, but then, you flip it over the bowl and you're suddenly upside down.
Yeah, we completely tune those everyday optical anomalies out. We just treat them as background
We
noise.
really do.
But the mechanics driving those simple kitchen table illusions are the exact same principles of physics that allow optical engineers to explore the observable
Or
universe.
peer into microscopic cellular structures.
Exactly. It's
And,
all the same geometry.
and that is the mission for today's deep dive.
Yeah.
We are decoding the actual mechanics of visibility, reflection, and refraction.
Right.
The goal here is to understand how human engineering has managed to harness and, well, manipulate the geometry of light, essentially giving you a shortcut to understanding the invisible framework of reality happening all around you.
It's a big topic.
It is. Okay, let's unpack this, because before we can even begin to manipulate light, we have to pin down what we are actually manipulating.
Right. What is light?
Yeah, and for a long time, the scientific consensus was just to trust what our eyes tell us, that light travels in a perfectly straight line.
Well, I mean, it was a very logical assumption to make. We call this the ray model of light.
Right.
And the primary evidence for the ray model is just the existence of sharp, distinct shadows. Like if you place an opaque object in front of a light source, the light doesn't naturally wrap around the object to illuminate the wall behind it, right?
No, it just terminates.
Exactly. It leaves a crisp silhouette.
But the straight line assumption comes with a pretty massive caveat.
It does.
If you make that opaque object small enough, like approaching microscopic scales, light suddenly refuses to walk in a straight line.
Yeah, the rules just break down.
It bends around the edges of the obstacle, entirely abandoning that straight ray model in a phenomenon known as diffraction.
Right. And to account for diffraction, physicists basically had to adopt a wave theory.
Like ocean waves.
Yeah, you can conceptualize it like water ripples encountering a rock in a pond. The wave simply wraps around the obstruction and continues on its way.
Oh, okay.
And for a significant portion of scientific history, treating light as this electromagnetic wave perfectly satisfied our observations.
Right. But then things got complicated.
Very, because as we pushed into the 20th century and began observing light interacting with matter at the atomic level, the wave theory just completely deteriorated.
Wow.
Yeah, light started behaving as discrete packets of energy. Particles, which we now call photons, actually knocking electrons out of metals.
Which created a fundamental crisis in physics, right? I mean, if light behaves as a continuous wave when wrapping around microscopic objects,
Right.
but then acts like a stream of physical particles when striking a metal plate, it can't be both.
You'd think so, yeah.
Or rather, the modern quantum mechanical framework had to synthesize those two ideas, basically suggesting light has properties of both, depending on how you measure it.
Exactly, the wave-particle duality.
But, I mean, if light is this highly complex, dual-natured quantum phenomenon, why do we still learn basic straight-ray optics in school?
That's a good point.
Are we just using a convenient fiction? Like, is the straight ray just a useful lie? Because calculating quantum wave particle duality to design a pair of reading glasses is too complicated?
This raises an important question, actually, about macroscopic engineering versus quantum physics, because it's really just a matter of scale.
Scale.
Yeah. When we are designing everyday optical tools, mirrors, corrective lenses, or even massive reflecting telescopes,
Right.
the quantum effects are so infinitesimally small that they don't mathematically impact the geometry of the design.
Oh, I see.
The wavelengths of visible light are tiny compared to the physical size of a glass lens. So at that macroscopic scale, light propagates in a manner that is functionally indistinguishable from a geometric ray.
So we aren't ignoring quantum mechanics.
No, not at all. We're just applying the mathematical model that dictates the physical scale of the problem.
We're isolating the variable that actually matters for what we're building.
Exactly.
Okay, so adhering to that geometric straight line model, let's look at the absolute rules of reflection.
Let's do it.
When these light rays encounter a highly polished, opaque boundary, like a silvered mirror, they are forced to bounce.
Right, and they bounce with flawless geometric predictability. The fundamental law here dictates that the angle of incidence equals the angle of reflection.
So if a light ray strikes a flat mirror at a precise, say, 30-degree trajectory,
It will rebound at exactly 30 degrees in the opposite direction, every single time.
Okay, I understand the geometry of a flat plane. It creates an image that is virtual, erect, and laterally inverted, which is why your left hand appears as your right hand in the mirror.
Right, standard bathroom mirror stuff.
But the physics become infinitely more useful when we curve the boundary.
Oh, absolutely.
And if you want to see this physics in action right now, like we said earlier, just look at a shiny spoon.
It's the perfect example.
It provides two entirely different optical tools depending on which side you guess.
Yeah, let's examine the concave side first, the inside bowl of the spoon.
Okay.
Concave mirrors are converging devices. Because the surface curves inward, when parallel rays of incoming light strike the different angled points along that curve.
The geometry of reflection forces all those rays to bounce inward.
Exactly. They cross paths at a specific unified coordinate called the principal focus.
Which means we can actually weaponize the energy of the light?
Weaponize is a strong word, but yes.
Well, I mean, if you take a concave mirror and point it at the sun, all those parallel rays of solar energy are converged onto a single millimeter of space.
Right.
If you place a combustible material like paper at that exact principal focus, the concentrated heat will ignite it.
It's basically a laser-like fire starter, and that converging mechanism is foundational to modern infrastructure. Yeah, we use it in reverse as well. If you place a light bulb exactly at the principal focus of a concave mirror, like the reflector in a car headlight or a searchlight,
Oh, I see.
the light shines backward into the bowl, and the mirror bounces all those scattered rays straight forward into a tight, parallel penetrating beam.
That's how headlights work.
Yeah. And we scale that exact same geometry up to build massive solar furnaces. We use giant fields of concave mirrors to focus enough solar radiation to actually melt steel.
Melt steel?
Yeah.
Just from bouncing light. That's incredible.
Just geometry.
But then you flip the spoon over and you get the opposite effect.
Right, the convex side.
It bulges outward. And instead of converging the light to a physical point, a convex surface scatters the parallel rays outward. They diverge into space.
Exactly.
But if our brain attempts to trace those scattered rays backward into the mirror, they appear to originate from a single focal point behind the glass.
Right, and that creates what we call a virtual image. Convex mirrors always produce an image that is erect, right side up, but significantly diminished. It's shrunken down.
So if the image is smaller and entirely virtual, what is the practical engineering value there? Like, why scatter the light instead of focusing it?
Well, it really comes down to human biology. The human eye has a limited degree of arc, right? We can only see so much of the world at once.
Okay.
By shrinking the reflected image, a convex mirror forcibly compresses a much wider physical area into a smaller visual field.
Oh, which is why they are the standard for vehicular rear view and side mirrors.
Exactly.
You don't necessarily need the car in the lane next to you to appear in its true life-size scale. You just need the widest possible spatial awareness of the highway.
Right. You want to see the whole lane, not just a life-size door handle. And there's a famous architectural installation at the Agra Fort in India utilizing this exact mechanism.
Oh, I've heard of this.
Yeah, they mounted a very small convex mirror on a high wall. And because of that diverging compression, an observer standing in the right position can view the entire massive structure of the Taj Mahal reflected within just a few inches of glass.
That is fascinating. But here's where it gets really interesting to me. All of this manipulation, whether concentrating heat to melt steel or compressing a landscape into a tiny mirror, it's built on mathematical certainty.
Right. It's not trial and error.
Optical engineers map these curves using the new Cartesian sign convention, which connects the physical curves to algebraic coordinates.
Yeah, it's a very elegant spatial relationship.
They place the absolute center of the mirror, which they call the pole, at the 0, 0 origin point of an XY axis.
And by establishing that origin, the geometry translates into a standard algebraic equation known as the mirror formula.
Which is 1 over v plus 1 over u equals 1 over f.
Exactly. You take the reciprocal of the image distance and add it to the reciprocal of the object distance, which equals the reciprocal of the focal length.
Okay, that sounds like a lot of math.
Well, the beauty of it is that because distances to the left of the mirror are plotted as negative numbers and distances to the right or behind the mirror are positive.
Oh, engineers can calculate the exact coordinate of a reflection.
Right. They don't have to build the mirror to see what it will do. They can mathematically prove whether an image will float in the air as a real projection or appear trapped behind the glass as a virtual illusion.
That is incredibly precise.
It is.
Okay, so we've completely mastered bouncing light. But things get considerably more complicated when light doesn't hit an opaque roadblock.
Yes, they do.
When light strikes a transparent medium like water, glass, or a diamond, it doesn't bounce. It enters the material and its trajectory violently
Right,
bends.
this is refraction.
Refraction. And this is the mechanism causing the pencil to look severed in the water glass or the floor of a swimming pool to appear dangerously shallow.
Exactly. And to understand the bend, we really have to address the fundamental speed limit of the universe.
The speed of light,
Right. In a pure vacuum, an electromagnetic wave of light travels at an absolute constant, roughly 300 million meters per second.
which is unfathomably fast.
Hmm.
But that constant only applies to a vacuum. When
Mhm.
light crashes into a physical medium like water, it actually slows down.
It does.
And I want to pause here because this often confuses people. If the speed of light is the universal constant, how does a simple glass of water slow it down? Does the photon itself lose velocity?
That's a great question. The photon itself always travels at the speed of light between the atoms.
Okay.
But a transparent medium is packed with atoms, and those atoms have their own electromagnetic fields. So as the light wave enters the material, it interacts with the electron clouds of those atoms.
I see.
The wave is continuously absorbed and re-emitted by the electrons. This endless chain of microscopic interactions creates a slight phase delay. And the cumulative effect of those billions of tiny delays is that the overall wave propagates through the material at a slower overall velocity.
So it's basically an atomic obstacle course,
That's a perfect way to look at it. And we measure that delay using the refractive index.
which is the ratio of light speed in a vacuum versus its speed in the medium.
Right, exactly. Water has a refractive index of 1.33. Standard crown glass is 1.52.
And diamond is a whopping 2.42, meaning light is crawling through a diamond at less than half of its vacuum speed.
Right. But we must separate the concept of optical density from physical mass.
Okay, let's unpack that.
The density of the electron clouds dictating the refractive index has absolutely nothing to do with the gravitational mass of the material.
This is a crucial distinction, because if you pour kerosene and water into a container, the kerosene floats on top because its mass density is lower, right? It is physically lighter.
Right.
But kerosene has a higher refractive index of 1.44 compared to water's 1.33.
Exactly. So to a propagating wave of light, the structurally lighter kerosene is actually a denser, more difficult obstacle course.
Wow.
Yeah, the light will experience a greater reduction in velocity passing through the floating kerosene than it will through the heavier water beneath it.
That is wild. Okay, so what does this all mean? I understand the speed reduction now, but how does slowing down mechanically force the straight ray to bend and change its physical angle?
It's all about the angle of approach.
Right, and the best analogy I've found for this is visualizing an axle with two wheels rolling on a smooth paved highway.
I love this analogy.
So the highway is the air, where the wheels are moving at maximum velocity.
Right.
But suddenly the wheels approach a boundary at a diagonal angle, and the surface changes to thick, sticky mud.
And the mud is the glass.
Exactly.
Wow.
Now, because of the diagonal approach, the wheel on the right strikes the mud first,
Right.
and it instantly loses speed due to the friction of the mud. But the left wheel is still on the smooth pavement.
Still traveling at maximum velocity.
Right. So because one side of the axle is moving significantly faster than the other, the entire axle violently pivots and swerves into the mud. The trajectory changes.
And that is exactly what happens to the wavefront of light when it strikes an optically denser medium at an oblique angle.
The wave actually swerves.
Yes. The side of the wave that enters the glass first slows down, while the rest of the wave is still speeding through the air, forcing the way to physically bend.
That makes so much sense.
And what's fascinating here is how the classic rectangular glass slab experiment perfectly demonstrates the mechanics of this pivot.
How so?
Well, when you fire a light ray at an angle into a flat glass slab, it hits the boundary, the right wheel hits the mud, so to speak, and the ray bends inward, angling closer to a perpendicular line we call the normal.
Okay.
It travels through the dense glass on this new angled trajectory.
But the slab has two sides. Eventually, the ray hits the exit boundary and transitions back out into the air.
Right, and the reverse mechanical pivot occurs.
The right wheel hits the pavement again.
Exactly. The right side of the wavefront exits into the air first and accelerates, while the left side is still delayed in the glass, so the ray aggressively pivots outward, bending away from the normal.
So it bends in, then bends back out.
Yes, and because the entry and exit walls of the rectangular slab are perfectly parallel, The inward geometric bend is completely mathematically canceled by the outward geometric bend.
Really?
Yeah. The light ray emerges traveling in the exact same parallel direction it started, but it has been physically displaced, just stepped several millimeters to the side.
It's a lateral shift.
Precisely.
And human engineering took that lateral shift and completely evolved it.
Oh, we did.
Because once optical physicists realized that specific transparent materials dictate precise mathematical delays in the speed of light, they realized they didn't have to settle for flat boundaries.
Right. We didn't have to just shift the light to the side. We could physically sculpt the glass, creating curves that forced the light to bend exactly where we dictate.
We engineered the lens.
Enter the lens. A lens utilizes the same geometric principles as our spherical mirrors, but instead of bouncing light off a curve, it relies on refraction to steer light through a curve.
Okay, so let's break down the two main types. A convex lens is thicker in its center and tapers at the edges. And because light passing through the thick center spends more time in the slow glass than the light passing through the thin edges, the convex lens operates as a converging device.
Exactly. It bends parallel rays inward to a principal focus. Just like the concave mirror, a convex lens can focus sunlight to a point and burn a hole in paper,
And then the concave lens is the opposite. It has a thin center and thick edges.
which causes the light passing through the periphery to be delayed longer. This forces the light rays to diverge and scatter outward, which always creates a virtual, shrunken image of the object.
Now, to measure the optical strength of these curves, like how violently they force the light to bend, engineers calculate the power of a lens, right?
Yes, utilizing a unit of measurement called dioptries, with a D.
Dioptries. And the mathematics here are remarkably elegant. The power is simply the reciprocal of the focal length in meters.
So P equals 1 over F.
Right. So if the lens forces the light to converge sharply over a very short distance, it possesses a high dioptry power.
Exactly. And the utility of dioptries over standard focal length measurements is why opticians use them. Optical power is strictly additive.
That is so cool.
Yeah. If you place a convex lens physically against another convex lens, you do not need complex calculus to predict the new focal point. You simply add their respective dioptries together to calculate the combined refractive power.
Which fundamentally explains the mechanics of an optometry exam.
It does.
I mean, when you go to the eye doctor and you're looking through that heavy metal machine, the phoropter and the doctor is rapidly flipping lenses down over your eye, asking number 1 or number 2.
Right, they aren't doing complex optical calculus in their head.
No, they're just calculating simple addition. If they test a plus 2.0 dioptry lens and then drop a plus 0.25 dioptry lens over it, the total converging power is just plus 2.25 dioptries.
It's brilliant.
They're literally stacking glass to find the exact algebraic power required to bend the light perfectly onto your retina.
And if we connect this to the bigger picture, extrapolate that additive property to industrial engineering, it is the foundation of high-precision optics.
How so?
Well, a major hurdle in lens manufacturing is chromatic aberration. Because white light is a spectrum, and different colors possess different wavelengths, they don't refract equally.
Oh, right.
Blue light actually bends at a slightly sharper angle than red light.
So a single convex lens inadvertently acts like a prism.
Exactly. It focuses the blue light slightly closer to the glass than the red light, meaning a single lens can never produce a perfectly sharp image. The edges will always be blurred with rainbow halos.
Which is terrible if you're building a microscope.
Or a telescope.
Yeah.
So to solve this, engineers exploit the additive nature of lenses. They create what's called an achromatic doublet.
The doublet.
Yeah. They take a convex lens made of crown glass, which converges light and separates the colors, and they physically bond it to a concave lens made of denser flint glass.
And the flint glass diverges the light just enough to force the blue and red wavelengths back into alignment.
You got it. They calculate the competing diopter powers to basically cancel out the physical defects of the single glass lens.
Wow.
Stacking different shapes and densities of glass to micromanage the phase delays of varying wavelengths. That is exactly how we engineer the complex lens arrays inside high-end cameras, biological microscopes, and orbital telescopes to explore the universe.
It is just a stunning escalation of engineering.
It really is.
I mean, we started by wrestling with the quantum identity of light, realizing we could set aside its wave-particle duality to just focus on its macroscopic geometry.
Right.
We mapped the angles of reflection, utilizing curved mirrors to converge solar heat or compress the visual field of a highway.
All mathematically proven.
And then we mapped the phase delays of refraction, utilizing the exact mathematical index of how different atoms slow down the universe's ultimate speed limit, which allowed us to sculpt glass that corrects the biological failures of our own eyes.
It's amazing. But that concept of the refractive index, that extreme slowing of light, it actually points toward a fascinating intersection with relativistic physics that we haven't even touched on.
Oh, where does relativity come into this?
Well, we established earlier that in a vacuum, the speed of light is the fundamental constant, right?
Right. 300 million meters per second.
And Albert Einstein's theory of relativity demonstrated that the speed of light and the flow of time are inextricably bound together. Space and time are a single fabric, and the speed of light is essentially the thread holding it tense.
Okay, but we just discussed that light doesn't travel at that constant when it enters a dense medium. It slows down drastically.
Exactly. Remember the diamond.
Yeah, refractive index of 2.42.
Right. The atomic structure is so dense with electromagnetic interference that light literally crawls through it, relatively speaking.
Wow.
So if the speed of light dictates the temporal framework of the universe, and light is experiencing such a massive phase delay inside the crystalline lattice of a diamond,
Wait, are you saying...
one could argue that the light trapped bending inside that gemstone is technically interacting with the flow of time differently than the light traveling through the air around it.
Oh my God.
Yeah.
That fundamentally shifts how you look at everyday objects.
It's a tiny optical illusion of space and time resting right on your finger.
An engagement ring isn't just a piece of compressed carbon. It's a microscopic zone where the electromagnetic waves defining our reality are severely delayed.
A localized disruption of space and time, something to ponder the next time you look at a piece of jewelry.
That is just, it forces you to realize that visibility itself is just our brain's interpretation of these delays and bounces.
Exactly. The physical world is entirely mediated by how light interacts with electron clouds before it ever reaches our optic nerve.
What a profound concept to ponder the next time you're sitting at a diner, looking at that fractured straw in a glass of water and realizing you are witnessing a fundamental shift in the velocity of reality.